Alright, welcome to the 3.1 section notes. Now there is another note page in front, just kind of a shout out to this. This is what we call your objective tracker. It just kind of has an overview of the whole chapter. Okay, so I usually bypass this in the videos, but if you have any questions on it, come see me in person. Alright, 3.1 is gonna sound surprisingly 8th grade. It is meant to be sort of an introductory chapter, or introductory section, pardon me. It is supposed to put us all on the same level. Okay, so in math, there's a lot of different ways you can define things, and so we just want to make sure we're all using the same definition. So if it's really boring and you know all this already, whatever, then you can bypass some stuff. But the whole point of this section is to make sure that we're all under the same terminology. We're all using the same terminology. Okay, so 3.1 is the rectangular coordinate system. First thing we're going to talk about is interpreting a line graph. My stylus is getting sticky. Okay, so interpreting a line graph. Here we have a line graph that's spending in billions of dollars. It looks like it's going from 1997 to 2003. Over here we have the question, how much was spent on medication in 2002? So it looks like this is the spending graph for medication from the years 1997 to 2003. Now, in order to answer this question, how much was spent on medication in 2002, we're going to have to read this graph. Something that always happens with PDFs, I don't know why, but these always get like shifted. So that goes to there, and that goes to there, and that goes to there, and that goes there. So we'll go over to 2002, which is right here, and we will head up this graph and to where it connects, which would be right about there. Sorry, my stylus is really sticky today. There we go. Okay, so it intersects this line right about here. Now what this line tells us is that in 2002, we see it's connected to 1400. So 2002, 1400. That would not be our answer though, right? Because 1400 doesn't make any sense. 1400 is a free-floating number. We want to make sure we put some units on that. So that would be $1,400. Is it though? Is it $1,400? I think it would actually be $1,400 billion because this graph is labeled that way. $1,400 billion is a little awkward, though. We could also say up 1.4 trillion. And we could say the same thing, right? I'd probably go with the second option. It's just a little better. So that is how you read a line graph. So that's just kind of introductory. Here's where we're going. This next thing we're going to talk about is ordered pairs. Now on this line graph, we have an ordered pair. We have the ordered pair 2002, comma, 1400. And this is kind of where you can tell the difference between real life and math class. Math class, as I will call it throughout the whole year, math is a different language. It is. We've talked about this, or we will talk about this shortly. It is a different language. It is the same amount of work as learning Spanish, as learning Japanese, as learning German. You have to be able to realize that they're two different things. So this point I have right here, this 2002, 1400, is very different from saying in 2002 we had $1.4 trillion spent on medication. And that's a really big distinction here we want to make. The point of this class is to start off getting very, very good at the math language, the math tools, the math workings, but more importantly, being able to take those once we know them and have solidified them and use them in real life. So we're going to basically learn 2 languages this year. We're going to learn as many things about the real world and the context with as many things about algebra we can, but also putting them in the real world. So usually we'll have some sort of word problem for everything. Okay, so we kind of talked about this math class thing, the 2002, 1400 ordered pair. Let's talk a little bit more about ordered pairs. We'll jump down here. Ordered pairs are called coordinates. Same thing, but it is just that is a coordinate pair. It's an ordered pair because there are two of them. There's always an x, comma, y. And over the years, throughout your education, you've probably seen some instances where you should turn it around, like with inverses, or you want to find one, not the other, whatever. But no matter what, we always write it as x, comma, y, with parentheses around it, comma in between. That indicates a point on the graph. There is no switching of those. X, comma, y. So let's go ahead and figure out some actual coordinates here. We have our x-axis and our y-axis. This is always the x-axis. And this is always the y-axis. I actually recommend a little bit kind of not calling it the x and the y because dropping off the word axis makes it super confusing when you're talking about the difference between a line and an axis. We're going to talk a lot more about this at the end of the day, or the end of the section either today or next time. But the x-axis is really what it's called, not the x. Normally I'm not super like hung up on namings and stuff because I mean as long as I know what you're saying it's okay, but with that kind of it's leading you down the rabbit hole, so just be careful with that. So this is the x-axis, y-axis. This point right here, A right here, looks like it's 6 over on the x-axis and 3 up, so we would call that coordinate 6, 3. Alright, cool. Let's do the same thing with B and C and D now. B goes back 8 and up 7. Now back 8's kind of hard to write, so instead maybe I'll go -8, but up a +7. It's not it's not meant to be a trick, right? Back, to the left would be negatives, down would be negatives, to the right's positives, ups would be positives. Alright, C is 3 back. Notice I'm kind of always just starting with left and right instead of up and down, just because I remind myself it's x, comma, y. So back 3 and down 5. Is that 5? Yeah. 1, 2, 3, 4, 5. Yep, so back 3, down 5 would be -3, -5. And then over here, over 3 and down 2 gives me a +3, but a -2. All right, and that's how you would find the coordinate or the ordered pair for each dot, each point. Okay. All right, before we move on though, let's talk about where these ordered pairs are existing. These points are existing in what we call a quadrant. Each one of them has been conveniently placed into different quadrants. We can look at that. Notice these Roman numerals here. They are our 4 quadrants. Think quadrant, quarters of the graph, right? And yes, it was just kind of decided for simplicity's sake that we always go counterclockwise around the coordinate plane. So A is sitting in quadrant 1, which we would write as a Roman numeral I. B is quadrant 2, which we would write as Roman numerals II, 2 I's. C is in quadrant 3, which would be, shocker, 3 I's. And quadrant D is in quadrant 4, which we would write as IV. Now, Roman numerals, why don't you just write 4 I's? It's because it's not tally mark system. This last one, V is 5, and then 1 in front means 1 away from 5, so that would be 4, right? 5 would be V, 6 would be VI. You may be like, well, why do I have to write Roman numerals? That's not fair. If you don't write Roman numerals, it gets very confusing as to whether you're listing an X, a Y, or a coordinate. See that? So, I don't want to mix it up with my point at all. So I want to make sure you use Roman numerals. Also, fun fact, if you don't know the Roman numerals, you don't know what Super Bowl it is. You don't want to look like an idiot at the Super Bowl party. So make sure you know your Roman numerals. All right. So that's our quadrants. And that's our points. Moving right along. Remember, at any point, if you have a question and you're like, I really don't get this, you're welcome to go back, watch it again. But the best thing you can do is probably just shoot me an email or a Canvas message, and I'd be happy to go over anything with you that's not just about this, that's about any point in the video. Feel free to shoot me an email. All right, moving right along. So what are we going to do with these points? These points, free floating in space, they're kind of like, okay, cool, so what, right? What happens when you have a bunch of points that follow a pattern? Right, let's pretend I have another coordinate graph over here, and I have a bunch of points that kind of go, I'm going to try and make this good as I can. A bunch of points that are forming some sort of pattern. Well, this pattern can create what we call a line, right? So if you have, and there's many different types of lines and curves, right? We've seen them over the years, but right now we're going to kind of focus on line patterns. If you have a pattern of these dots all in a row, well, then that means there's some sort of hidden math going on there, okay? Now, a line on a graph does not have points on it, okay? It's a weird way to think about it, but a line on a graph does not have points on it. A line on a graph is a bunch of points. Okay, if you were to zoom in infinitesimally on a line, what you would see is not a line. You would see a bunch of itty bitty little dots of what we call solutions all next to each other. And this is something that even myself, I had to like kind of figure out in college. I never once thought about the fact that a line is not a line on the graph. It is not a line. It is not a continuous line. Now it is. Don't get me wrong. I'm not saying there isn't a line on the page there because I see it. But if you think hard enough, this is just a bunch of dots. An infinite amount of dots put together. And that makes the line. It is not a line. So where are these dots coming from? What is it that these dots all have in common that they're creating this line? That's where we get an equation. The dots are created by an equation. The line is created by the dots. Okay, and many people often miss that step in the middle, and that's what makes kind of relating equations to lines so confusing. Because what's happening is you're having lots and lots of little dots. You're having lots and lots of coordinate pairs, and the coordinate pairs are all following a certain equation, okay? Now this is not the equation for this line. This equation is actually down here, okay? But what do we call each one of those individual dots? We call each one of those individual dots a solution. And it is the collection of all the possible solutions to this math. We're just call it math, right? Because that's all it is multiplication and addition. This equation, this math, all the possible answers to that are creating this line. Okay, so think of it like a pie contest, okay? You have every single type of pie in your pie contest. You would have all the pies, right? In this case, we're talking about dots. I'm having all the kind of dots that fit this definition of quote-unquote pie, right? In order to be a pie, you have to have a certain number of things, right? You have to have a crust. You have to have a filling. You have to have, a pan. I don't know. You have to, not very many things in pies, right? But you basically have to have a crust and a filling. You have both of those, you're considered a pie. But that doesn't mean there's only one type of pie, right? There's an infinite amount of pies. You can change recipes in so many ways to make pie. But they all have to be pie. So same thing here. All of the points here, all the solutions have to fit the math, but there's an infinite number of them. Okay, so let's look at just a specific example, kind of take it back to kind of something we can solve. If we have this equation, 2x plus 3y equals 6. Okay, and then x is a number, y is a number. I'm looking for the solution pairs that would match this, right? If I tried just any number in the universe, it might not work, right? Let's just pick the easiest one, 0, 0. Let's just pick 0, 0. So is 0, 0 a solution? Not really, because when I plug that in for x and y, that does not equal 6. You see that? 0 does not equal 6. And so 0, 0 is not a solution. It's not considered a pie, right? In order for it to be a solution, the math has to work out. So whatever's happening on the left-hand side, it has to equal the right-hand side. So let's kind of fill in the blanks now. If I knew that negative 3 was x, then what y would actually make it equal 6? That's kind of our question here. So 2 times negative 3 plus 3y equals 6. So that's the question now. What y is actually going to make this work? What y would make this solution be true? Negative 6 plus 3y equals 6. Add 6 to the other side. Oh, one thing on the videos is I don't write a lot of the solving of equations, mostly because I don't have room. If you have problems with solving equations, come see me. Totally fine. All I did in this one was add 6 to both sides. Okay, so I'm not going to write add 6, add 6. You're welcome to do that on yours. I do not have the room. So, so we divide by 3 here. Y equals 4. So in order for this to be a solution pair, y has to be 4. Can't be 5, can't be 2, can't be 3, can't be 4.1, it has to be 4. Alright, let's go find the other one. So this one kind of flips same argument, different side though. What x do we need to make this solution pair true if y is negative 4? Same idea, we'll go over here. 2x plus 3 times negative 4 equals 6. Okay, notice I didn't plug it in the x because it is sitting in the y spot of the xy pair, right? That spot means something. You can't just choose which one seems more convenient to you. Okay, you actually have to plug it into the right one. 2x minus 12 equals 6. 2x equals 18. So it looks like x equals 9. But an x equals 9 is not my answer. That's not what they asked before. They asked if I had the solution. The solution would be 9 comma negative 4. That would be my answer. Okay, so now what are these things? Well, down here we have the solution graph, right? And if you look at it, it looks like a line. But if we were to zoom in infinitesimally, we'd see a whole bunch of dots. In fact, we would see the dots 9, negative 4, which would be like crazy over here, and then down there, right? Sorry, down there. Oh my goodness. Okay, so like right there. And then if we saw back 3 and up 4, right there. So you see how both these dots, we found them to be true in the equation. We found the ones that were true. The one we tried and didn't make sense, 0, 0, is not on this line because it doesn't fit the math, right? It's not on the set of all dots. So what we have found is the set of all dots. We found 2 of them that happen to be on there. Do we need to find all of them? No. 2 dots make a line. That's totally fine. We can just connect the dots and assume the other ones will work out. But it doesn't matter. We could check any of them and they would work out as long as they were on the line. Alrighty. So let's talk next about 2 certain points that many people love to spend many, many years on, but in reality they're really kind of not that special. They're maybe mostly just convenient. They're called the x and y intercepts. Okay? You have definitely talked about this at least once. Definitely at least once. The x and y intercepts are easy to remember what they are, but they're hard to remember how to find them, how to use them, and where, like, what they look like. X and y intercept. Most people remember that's the place where you cross the x-axis. X-intercept. The word intercept, I know what that means because I've driven before. I've driven with my parents, and that means intersection, right? So crosswalk, crossing. Oh, okay, it's the place where it crosses the x-axis. I can remember that, right? Same thing with y. That's the place where it crosses the y-axis. Woot. Sweet. Most people remember that. And if I show you the graph up here of that same equation, you could very easily pick out the x and y intercepts. What people don't remember, and actually is arguably more important, is what these things always look like. Y-intercepts always look like 0, comma something, and x-intercepts always look like x, comma 0. Okay? And it's the 0 part of that makes it super convenient. The fact that it's hitting an axis means in one aspect you haven't gone left or right or up or down, right? In a y-intercept, we haven't gone left or right. So this is always going to have a 0 in front of it. And then in this case, a 2. 2 up, right? But in the other one, in an x-axis, we have not gone up or down. And so while this is 3, in this case it doesn't really matter, it's going to always have a y of 0, right? We have not moved y. That's why it's hitting the x-axis. We have not moved x. That's why it's hitting the y-axis. And so that's where it gets super convenient. We have a bunch of zeros, and 0 is a great number. I know many people disagree the higher up in math they go because it causes problems when you try to divide or take square root or whatever, consider it positive or negative, but in linears especially, when we have to multiply and add all the time, 0 is a great number. So finding the x and y intercepts is a great idea because it can actually help you graph. They're probably the easiest ones to find. So we're going to find the x and y intercepts, we're basically going to apply the ideas of 3.1. okay, the example 3.1 here, we have part of a solution, we're going to go find the other half. Okay, so let's start with this one. 3.2, 5.2. 5, I don't know why that's labeled 5.2. Oh yeah, I do. Objective 5. Okay, here's our equation. Sorry, I derailed there for a minute. 4x minus y equals negative 3. Now they want me to find the x and y intercepts, but really what they're saying is, here's two half solutions. Go find the other half. We just did that twice, right? And so this is just, that's what I meant by they're not that special. Okay, they act like any of the other points, they just happen to occur in a place that might be convenient to us. Okay, all right, so let's plug them in. I'm not going to tell you which one's which right now because, I mean, you know, but it doesn't really matter because I'm just plugging in 0. All right, plug in 0 for, in this case, x minus y equals negative 3. And notice that is super convenient because what's 4 times 0? 0. It just drops away. So negative y equals negative 3 or y equals 3. Didn't have to multiply or subtract or anything. Like things drop away, right? Okay, let's do it again. This time, y is 0. All right. Also super convenient because that's just going to drop away. Whoops. 3 got funky. Alrighty, and now we just divide by 4. Yeah, it ended up as a fraction, and that's okay. It's going to happen a lot. Welcome to a college class. Sorry. Things in real life do not work out perfectly, but honestly, that's really not even the biggest deal here because I'm just going to use it to eyeball anyway. So you could write it as a decimal. I don't care. Totally fine. Write it as a decimal. I would say get comfortable with fractions because we're going to spend an entire unit on them with rationals, but yeah, it's really not that important right now. Okay, so some pitfalls that I see with this one. Do not try to combine this idea in any way, shape, or form. Think of it as two separate problems. First find the x-intercept, then find the y-intercept. You're not going to take the 3 that we found from the y-intercept and plug it in for the x-intercept. You're not going to have the point 3 comma negative 4/3 or negative 4/3 comma 3, okay? You'd need them to be two separate points because they are two separate points. Any sort of combination here would not yield a correct answer, first off. And at the end of the day, that's the most important thing. I don't care how you do stuff, but you got to do it right. Okay, you got to get it right. But you also need 2 points to graph a line. We can't graph a line without at least 2 of the points, bare minimum. Now you can have 3, 4, 5, whatever you want, but you need at least 2. So here I have 2 separate points now. I have one at 0, 3. And like I said before, yes, that's a fraction, but really all I need to do is go back about 3/4 of the way, whoops, and stay on 0. And those are my 2 points, and that's all I need. Oh, geez. To graph the line. Fun fact, I'm doing this on my phone, so my lines will never be perfect, and I'm not going to waste 20 minutes trying to make them perfect. So, okay, that is how you would graph an equation with x and y intercept. Arguably, yes, there is probably a faster way to do that. Okay. Again, like, I don't really care how you're going to graph something because at this level, it just needs to be right. Okay, but if the question asks to find the x and the y-intercept and to graph the function, you better make sure you have all 3 pieces, right? If you go to your boss and he wants you to fill out the Johnson report, the William report, and the Jones report, and you only take one of them, he's going to be mad, okay? You need to make sure you do all of the instructions. If you want to graph this a different way, a way we will talk about in the next section, go right ahead. That's totally fine with me. But you've already found the x and y intercept, you may as well just plot them on the graph and connect the dots. Okay, so if you have to find the x and y intercept, this may be the fastest way to graph it. Okay, that's just my little public service announcement. Sometimes your teachers have been telling you have to do a certain way, and I do validate them for that. They have an end goal in mind. I sometimes will tell you to do it a certain way because I have an end goal in mind. I have something that I want to connect it to later. But as long as you understand how to do it and you're getting it right and it looks good and I can read it and it makes sense and it's logical, and you will get full points. Okay, that's totally fine with me. All right. Last thing we're going to talk about, nope, just kidding, two things we're going to talk about this section. Second to last thing. When I said watch out for labeling it the x and the y, right, instead of the x-axis and the y-axis, these next two examples are why. Or why I was concerned with that. Graph the line y equals 2. What? That's a little weird. There's no x there. How can there be solutions if there's no x there? Okay, same thing here. Graph the line x plus 1 equals 0. Where's the y? How do I solve for y when there's no y in the equation? So starting with this one, both of these kind of make a statement. Okay, they make a statement that says no matter what the other one is, y is 2. So if we were to make a little mini table, which you could also do, right? Kind of if you wanted to maybe organize your thoughts for here a little better, you could make a mini table and say x and y for, if x is 0, y is 3. If y was 0, x is negative 3/4. Tables are great. They work for absolutely every type of graph. Even if it's not a linear pattern we're going for, linear meaning line. They work for everything. Rationals, radicals, the crazy quadratic nonsense we're going to see later on, like cubics, fifth degrees, they work for absolutely everything. So tables are fabulous. However, they are time consuming. In this case though, no matter what x is, if I were to quote unquote solve for things, well then the equation tells me y is equal to 2. No matter the case. Really should be kind of a what's the word? Preemptive statement here. No matter what, y equals 2. That's really what it should say. No matter what, y equals 2. But mathematicians are going to find are incredibly lazy. So if you're lazy too, congrats, you're in the right class. No matter what, y equals 2. And that's it. Like, y equals 2. So if we were to plot all three of these points, we don't even have to. Like, we can just plot 2 of them. Here's the line y equals 2. And what we get is this horizontal line that's just floating around y equaling 2. See that? So it's kind of a special case. I hesitate to say that though because it's really not that special. I don't want you to think there's like, oh, there's like 7 million rules with all these special cases. No, it's just a weird case, right? It's just like this is something that is maybe making a slightly different statement. No matter what x is, y is 2. Okay, so same idea here, and at any point in the videos, I highly recommend that if we go to the next problem, you kind of pause it and try it on your own, especially if you were absent, because that's what we're going to be doing a lot in class. If you don't try it on your own, you sometimes really miss a great opportunity to kind of see what you actually know. And frankly, watching an hour-long video at home is really boring, so I really recommend you try it on your own. Okay, cool. This one also kind of making the same statement, but there's no y. But how do we interpret this statement? Kind of hard to do so unless we maybe solve for x by moving that x to the other side. So it's not always like right on the nose what the statement is, but you can make it on the nose, so just solve for that real fast. And then this is saying the same thing. No matter what y is, x was negative 1. Okay, cool. So if I had a little table, y, if I had 2, 4, oh geez, 2, 4, negative 12. No matter what y was, x was negative 1. Had to be. Alright, so if I were to plot all those, I would just go back to x equaling negative 1, and we would see a vertical line. And we would get a vertical line in this case. And again, not really a special case, just kind of a weird one. Something that you do probably want to commit to memory because it's really fast. But be hesitant about just memorizing it because if you recall, this is the y-axis, whereas this is the line x equals negative 1. Do you see how that's really tricky, right? We call the y-axis the up and down one, but the vertical lines are x. So find a way to help you remember that, some mnemonic device or something, but it's just, also you can just read it. The y-axis isn't named for the fact that it has the y's. It's not named for its relationship to the equation, right? It's named because that's where all the line y's are, right? The little tick marks are all y things. Anyway, don't think too hard about this. Just try to make sure you remember that the vertical ones are x, the horizontal ones are y. Or just plot one, make a table. Okay, cool. All right, the very last thing, we're going to try one more out. We're going to do it the same way. I think I'm going to find 2 points to graph this thing because points make a line. And 2 points that would seem super convenient to me would probably be the x, y-intercept, because I like 0. Alright, let's go plug in x equals 0, plug in y equals 0. In this case, that is not a requirement. I do not have to do that here. I could pick any points that I wanted to in the entire known universe and they would still work, okay? But here, I like 0. 0 is convenient for me. 0 drops things away. So, x plus 2y equals 0. And in this case, we are going to change x to 0. Come on. Okay, so 2y equals 0. And yes, I am more than welcome to divide 0 by stuff. Can't just divide by 0. So 0 divided by 2 is 0, right? Because 0 times 2 would be 0. And so y equals 0. Okay, cool. All right, got one. Now I just need the other one. So now x plus 2 times 0 equals 0. And then we got x equals 0. Do you see how convenient that was? Because 2 times 0 is just 0 and it goes away. All right. Uh-oh. What's the problem here? Turns out that both my x and y-intercept are the exact same point. And I probably could have seen that from the first one, but, maybe I didn't. So I'm left with kind of this dilemma that I need 2 points, but I only have 1. It's not really a dilemma, though, because I just mentioned that I can use whatever I want. This is just a certain convenient point for me. So instead of 0, no, let's use 1. Let's go do the 3.1 problem that we did at the very beginning, right? Plug in 1. Because why not? Let's see, subtract that. We get 2y equals -1, so y equals -1/2. And again, if that part's tripping you up over and over again, come see me, shoot me an email. We'll be happy to do something real fast, because it's usually only like a tiny little bit that you need. You're going to find I'm really not that scary, I promise. I'm a little jokey, but I'm not going to hurt you. Come see me, and we will fix that. So 1/2, -1/2. Not the prettiest point, and that's going to happen more often than not. You're going to get not pretty points if you just go choosing randomly. Maybe if you do more, practice with it, you can get more of an intuition. Math is never a spectator sport, so you do have to practice regardless. But it's okay, though, because really I'm just going to go out 1 and down halfway. I can eyeball a half. It's not really that hard. And I've graphed my line. Oh, maybe. Nope. Try that again. Yeah, that one's pretty good. Okay, cool. Little technical note. Yes, you have to put your lines all the way to the end. Yes, you have to put the arrows. I don't care if they're ugly. Not doing that is actually incorrect. Okay, it's an incorrect statement. It's a huge pet peeve of mine, but that's beside the point. I know what they're going to expect of you at 1050, and 1050 is going to hammer you for that. So I don't want you to lose points over something silly like that. We're going to weed that out now. You must draw the lines all the way to the end, okay, or you will be docked points. All right, welcome to math class. That's basically where we're going to start. So graphing some lines. We talked about a few quote-unquote special cases. We talked about points and how they create lines. If you have any questions at all, shoot me an email.